Discrete Probability Chapter 7 with Question, Answer Animations Copyright McGraw-Hill Education. All rights reserved. No reproduction or distribution without the prior written consent of McGraw-Hill Education. Chapter Summary Introduction to Discrete Probability Probability Theory Bayes Theorem Expected Value and Variance. An Introduction to Discrete Probability Section 7.1. Section Summary Finite Probability Probabilities of complements and unions of events Probabilistic reasoning. Probability of an event. We first study Pierre-Simon Laplace's classical theory of probability, which he introduced in the 18th century, when he analyzed games of chance. We first define these key terms. An experiment is a procedure that yields one of a given set of possible outcomes. The sample space of the experiment is the set of possible outcomes. An event is a subset of the sample space. Here is how Laplace defined the probability of an event. Definition: if S is a finite sample space of equally likely outcomes, and E is an event, that is, a subset of S, then the probability of E is P E equals E S. For every event E, we have 0 P E 1. This follows directly from the definition, because 0 P E equals E S S S 1. Since 0 E S. Pierre-Simon Laplace, 1749–1827. Applying Laplace's definition. Example: an urn contains 4 blue balls and 5 red balls. What is the probability that a ball chosen from the urn is blue? Solution: the probability that the ball is chosen is 4/9, since there are 9 possible outcomes, and 4 of these produce a blue ball. Example: what is the probability that when 2 dice are rolled, the sum of the numbers on the 2 dice is 7? Solution: by the product rule there are 62 equals 36 possible outcomes. 6 of these sum to 7. Hence, the probability of obtaining a 7 is 6/36 equals 1/6. Applying Laplace's definition. Example: in a lottery, a player wins a large prize when they pick 4 digits that match, in correct order, 4 digits selected by a random mechanical process. What is the probability that a player wins the prize? Solution: by the product rule there are 104 equals 10,000 ways to pick 4 digits. Since there is only one way to pick the correct digits, the probability of winning the large prize is 1/10,000th equals 0.0001. A smaller prize is 1 if only 3 digits are matched. What is the probability that a player wins the small prize? Solution: if exactly 3 digits are matched, one of the 4 digits must be incorrect and the other 3 digits must be correct. For the digit that is incorrect, there are 9 possible choices. Hence, by the sum rule, there are a total of 36 possible ways to choose 4 digits that match exactly 3 of the winning 4 digits. The probability of winning the small prize is 36/10,000 equals 9 2,500 equals 0.0036. Applying Laplace's definition. Example: there are many lotteries that award prizes to people who correctly choose a set of 6 numbers out of the first n positive integers, where n is usually between 30 and 60. What is the probability that a person picks the correct 6 numbers out of 40? Solution: the number of ways to choose 6 numbers out of 40 is C. 40, 6 equals 40, 34, 6 equals 3,838,380. Hence, the probability of picking a winning combination is 1,3,838,380 at approximately equals 0.00000026. Can you work out the probability of winning the lottery with the biggest prize where you live? Applying Laplace's definition. Example: what is the probability that the numbers 11, 4, 17, 39, and 23 are drawn in that order from a bin with 50 balls labeled with the numbers 1, 2, 50 if the ball selected as not returned to the bin? The ball selected as returned to the bin before the next ball is selected. Solution: use the product rule in each case. Sampling without replacement, the probability is 1/254,251,200 since there are 50, 49, 47, 46, 45 equals 254,251,200. B. Sampling with replacement, the probability is 1/550 equals 1/312,500,000 since 505 equals 312,500,000. The probability of complements and unions of events. Theorem 1. Let E be an event in sample space S. The probability of the event equals S minus E. The complementary event of E is given by proof using the fact that equals S minus E. The probability of complements and unions of events. Example, a sequence of 10 bits is chosen randomly. What is the probability that at least one of these bits is 0? Solution. Let E be the event that at least one of the 10 bits is 0. Then is the event that all of the bits are 1s. The size of the sample space S is 210. Hence, the probability of complements and unions of events. Theorem 2. Let E1 and E2 be events in the sample space S. Then proof, given the inclusion-exclusion formula from section 2.2. A B equals A plus B minus a B. It follows that. Example, what is the probability that a positive integer selected at random from the set of positive integers not exceeding 100 is divisible by either 2 or 5? Solution. Let E1 be the event that the integer is divisible by 2 and E2 be the event that it is divisible 5. Then the event that the integer is divisible by 2 or 5 is E1 E2 and E1 E2 is the event that it is divisible by 2 and 5. It follows that P E1 E2 equals P E1 plus P E2 P E1 E2 equals 50 100ths plus 20 100ths minus 10 100ths equals 3/5. The probability of complements and unions of events. Monty Hall puzzle example, you are asked to select one of the 3 doors to open. There is a large prize behind one of the doors and if you select that door, you win the prize. After you select a door, the game show host opens one of the other doors, which he knows is not the winning door. The prize is not behind the door and he gives you the opportunity to switch your selection. Should you switch? Solution. You should switch. The probability that your initial pick is correct is 1/3. This is the same whether or not you switch doors. But since the game show host always opens a door that does not have the prize, if you switch the probability of winning will be 2/3. Because you win if your initial pick was not the correct door and the probability your initial pick was wrong is 2/3. 132. This is a notoriously confusing problem that has been the subject of much discussion. Do a web search to see why. Probability Theory Section 7.2. Section Summary. Assigning probabilities. Probabilities of complements and unions of events. Conditional probability. Independence. Bernoulli trials in the binomial distribution. Random variables. The birthday problem. Monte Carlo algorithms. The probabilistic method, not currently included in the overheads. Assigning probabilities. Laplace's definition from the previous section assumes that all outcomes are equally likely. Now we introduce a more general definition of probabilities that avoids this restriction. Let S be a sample space of an experiment with a finite number of outcomes. We assign a probability Ps to each outcome S, so that I0 Ps1 for each S element of Se. The function P from the set of all outcomes of the sample space S is called a probability distribution. Assigning probabilities. Example, what probabilities should we assign to the outcomes H, heads, and T, tails, when a fair coin is flipped? What probabilities should be assigned to these outcomes when the coin is biased so that heads comes up twice as often as tails? Solution. For a fair coin, we have P, H equals P, T equals 1/2. For a biased coin, we have P, H equals 2P, T. Because P, H plus P, T equals 1, it follows that 2P, T plus P, T equals 3P, T equals 1. Hence, P, T equals 1/3 and P, H equals 2/3. Uniform distribution definition. Suppose that S is a set with n elements. The uniform distribution assigns the probability 1 and to each element of S. Note that we could have used Laplace's definition here. Example, consider again the coin flipping example, but with a fair coin. Now P(H) equals P(T) equals 1/2. Probability of an event definition. The probability of the event E is the sum of the probabilities of the outcomes in E. Note that now no assumption is being made about the distribution. Example, suppose that a die is biased so that 3 appears twice as often as each other number, but that the other 5 outcomes are equally likely. What is the probability that an odd number appears when we roll this die? Solution. We want the probability of the event E equals 1, 3, 5. We have P3 equals 2/7 and P1 equals P2 equals P4 equals P5 equals P6 equals 1/7. Hence, P(E) equals P1 plus P3 plus P5 equals 1/7 plus 2/7 plus 1/7 equals 4/7. Probabilities of complements and unions of events. Complements still holds, since each outcome is in either E or, but not both, unions. Also still holds under the new definition. Combinations of events theorem. If E1, E2 is a sequence of pairwise disjoint events in a sample space S, then see exercises 36 and 37 for the proof. Conditional probability definition. Let E and F be events with P, F greater than 0. The conditional probability of E given F, denoted by P, E, F, is defined as. Example, a bit string of length 4 is generated at random so that each of the 16-bit strings of length 4 is equally likely. What is the probability that it contains at least 2 consecutive zeros, given that its first bit is a 0? Solution. Let E be the event that the bit string contains at least 2 consecutive zeros, and F be the event that the first bit is a 0. Since EF equals 0000, 0001, 0010, 0011, 0100, P, EF equals 5/16. Because 8-bit strings of length 4 start with a 0, P, F equals 8/16. Conditional probability example. What is the conditional probability that a family with 2 children has 2 boys, given that they have at least 1 boy? Assume that each of the possibilities BB, BG, GB, and GG is equally likely where B represents a boy and G represents a girl. Solution. Let E be the event that the family has 2 boys and let F be the event that the family has at least 1 boy. Then E equals BB, F equals BB, BG, GB, and EF equals BB. It follows that P, F equals 3/4 and P, EF equals 1/4. Hence, independence definition. The events E and F are independent if and only if. Example. Suppose E is the event that a randomly generated bit string of length 4 begins with a 1 and F is the event that this bit string contains an even number of 1s. Are E and F independent if the 16-bit strings of length 4 are equally likely? Solution. There are 8-bit strings of length 4 that begin with a 1, and 8-bit strings of length 4 that contain an even number of 1s. Since the number of bit strings of length 4 is 16, since EF equals 1111, 1100, 1010, 1001, P, EF equals 4/16 equals 1/4. We conclude that E and F are independent, because P, EF equals 1/4 equals 1/2, 1/2 equals P, E, P, F, P, EF equals P, E, P, F. P, E equals P, F equals 8/16 equals 1. Independence example. Assume, as in the previous example, that each of the 4 ways a family can have 2 children, BB, GG, BG, GB, is equally likely. Are the events E, that a family with 2 children has 2 boys, and F, that a family with 2 children has at least 1 boy, independent? Solution. Because E equals BB. P, E equals 1/4. We saw previously that P, F equals 3/4 and P, EF equals 1/4. The events E and F are not independent since P, E, P, F equals 3/16 does not equal 1/4 equals P, EF. Pairwise and mutual independence definition. The events E1, E2 and are pairwise independent if and only if P A J equals P A P E J for all pairs I and J with IJN. The events are mutually independent if whenever ij, j equals 1, 2, m are integers with 1 I1 less than I2 less than I'm n and m2. Bernoulli trials. James Bernoulli, 1854–1705. Definition: suppose an experiment can have only two possible outcomes, e.g., the flipping of a coin or the random generation of a bit. Each performance of the experiment is called a Bernoulli trial. One outcome is called a success and the other a failure. If P is the probability of success and Q the probability of failure, then P plus Q equals 1. Many problems involve determining the probability of K successes when an experiment consists of n mutually independent Bernoulli trials. Bernoulli trials example: a coin is biased so that the probability of heads is 2/3. What is the probability that exactly 4 heads occur when the coin is flipped 7 times? Solution: there are 27 equals 128 possible outcomes. The number of ways 4 of the 7 flips can be heads is C, 7, 4. The probability of each of the outcomes is 2/3, 4, 1/3, 3 since the 7 flips are independent. Hence, the probability that exactly 4 heads occur is C, 7, 4, 2/3, 4, 1/3, 3 equals 35, 16, 27 equals 562,187. Probability of K successes in n independent Bernoulli trials. Theorem 2. The probability of exactly K successes in n independent Bernoulli trials, with probability of success P and probability of failure Q equals 1 minus P, is C, n, K, P, K, Q, n minus K. Proof. The outcome of n Bernoulli trials is an n-tuple T1, T2, Tn, where each is T either S, success, or F, failure. The probability of each outcome of n trials consisting of K successes and K-1 failures, in any order, is PKQn-K. Because there are C, N, K, n tuples of S's and F's that contain exactly K S's. The probability of K successes is C, N, K, PKQn-K. We denote by B, K, N, P, the probability of K successes in n independent Bernoulli trials with P the probability of success. Viewed as a function of K, B, K, N, P, is the binomial distribution. By Theorem 2, B, K, N, P equals C, N, K, P, K, Q, N minus K. Random variables. Definition: a random variable is a function from the sample space of an experiment to the set of real numbers. That is, a random variable assigns a real number to each possible outcome. A random variable is a function. It is not a variable, and it is not random. In the late 1940s, W. Feller and J.L. Dube flipped a coin to see whether both would use random variable or the more fitting, chance variable. Unfortunately, Feller won and the term random variable has been used ever since. Random variables. Definition: the distribution of a random variable x on a sample space S is the set of pairs R, P, x equals R for all Rx, S. Where P, x equals R, is the probability that x takes the value R. Example: suppose that a coin is flipped 3 times. Let xt be the random variable that equals the number of heads that appear when t is the outcome. Then xt takes on the following values: xhhh equals 3, xttt equals 0, xhht equals xhth equals xthh equals 2, xtth equals xtht equals xhtt equals. Each of the 8 possible outcomes has probability 1/8. So, the distribution of xt is P, x equals 3 equals 1/8, P, x equals 2 equals 3/8. P, x equals 1 equals 3/8, and P, x equals 0 equals 1/8. The famous birthday problem, the puzzle of finding the number of people needed in a room to ensure that the probability of at least 2 of them having the same birthday is more than 1/2 has a surprising answer, which we now find. Solution: we assume that all birthdays are equally likely and that there are 366 days in the year. First, we find the probability Pn that at least 2 of n people have different birthdays. Now, imagine the people entering the room one by one. The probability that at least 2 have the same birthday is 1 minus Pn. The probability that the birthday of the second person is different from that of the first is 365/366. The probability that the birthday of the third person is different from the other two, when these have 2 different birthdays, is 364/366. In general, the probability that the jth person has a birthday different from the birthdays of those already in the room, assuming that these people all have different birthdays, is 366 minus j minus 1. 366 equals 367 minus j, 366. Hence, Pn equals 365 366, 364 366, 367 minus n, 366. Therefore, 1 minus Pn equals 1 minus. Checking various values for n with computation help tells us that for n equals 22, 1 minus Pn approximately equals 0.457, and for n equals 23, 1 minus Pn approximately equals 0.50. Consequently, a minimum number of 23 people are needed so that the probability that at least 2 of them have the same birthday is greater than 1/2. Monte Carlo algorithms that make random choices at one or more steps are called probabilistic algorithms. Monte Carlo algorithms are probabilistic algorithms used to answer decision problems, which are problems that either have true or false as their answer. A Monte Carlo algorithm consists of a sequence of tests. For each test, the algorithm responds true or unknown. If the response is true, the algorithm terminates with the answer is true. After running a specified sequence of tests where every step yields unknown, the algorithm outputs false. The idea is that the probability of the algorithm incorrectly outputting false should be very small as long as a sufficient number of tests are performed. Probabilistic primality testing. Probabilistic primality testing, see example 16 in text, is an example of a Monte Carlo algorithm, which is used to find large primes to generate the encryption keys for RSA cryptography, as discussed in Chapter 4. An integer n greater than 1 can be shown to be composite, i.e., not prime, if it fails a particular test, Miller's test, using a random integer b with 1 less than b less than n as the base. But if n passes Miller's test for a particular base b, it may either be prime or composite. The probability that a composite integer passes n Miller's test is for a random b is less than 1/4. So failing the test, it is the true response in a Monte Carlo algorithm, and passing the test is unknown. If the test is performed k times, choosing a random integer b each time, and the number n passes Miller's test at every iteration, then the probability that it is composite is less than 1/4 k. So for a sufficiently large k, the probability that n is composite even though it has passed all k iterations of Miller's test is small. For example, with 10 iterations, the probability that n is composite is less than 1 in 1 million. Bayes theorem. Section 7.3. Section summary. Bayes theorem. Generalized Bayes theorem. Bayesian spam filters. AI applications, optional, not currently included in the overheads. Motivation for Bayes theorem. Bayes theorem allows us to use probability to answer questions such as the following. Given that someone tests positive for having a particular disease, what is the probability that they actually do have the disease? Given that someone tests negative for the disease, what is the probability that in fact they do have the disease? Bayes' theorem has applications to medicine, law, artificial intelligence, engineering, and many diverse other areas. Bayes' theorem. Bayes' theorem. Suppose that E and F are events from a sample space as such that P E does not equal 0 and P F does not equal 0. Then, example, we have 2 boxes. The first box contains 2 green balls and 7 red balls. The second contains 4 green balls and 3 red balls. Bob selects one of the boxes at random. Then he selects a ball from that box at random. If he has a red ball, what is the probability that he selected a ball from the first box? Let E be the event that Bob has chosen a red ball and F be the event that Bob has chosen the first box. By Bayes' theorem, the probability that Bob has picked the first box is Thomas Bayes, 1702–1761. Derivation of Bayes' theorem. Recall the definition of the conditional probability P, E, F. From this definition, it follows that continued derivation of Bayes' theorem. On the last slide we showed that continued solving for P, E, F and for P, F, E tells us that equating the two formulas for P, E, F shows that derivation of Bayes' theorem. On the last slide we showed that. Note that hence, since, because and by the definition of conditional probability. Applying Bayes' theorem example, suppose that one person in 100,000 has a particular disease. There is a test for the disease that gives a positive result 99% of the time when given to someone with a disease. When given to someone without the disease, 99.5% of the time it gives a negative result. Find the probability that a person who tests positive has the disease. The probability that a person who tests negative does not have the disease. Should someone who tests positive be worried? Applying Bayes' theorem solution, let D be the event that the person has the disease, and E be the event that this person tests positive. We need to compute P, D, E from P, D, P, E, D, P, E, P. So, don't worry too much if your test for this disease comes back positive. Can you use this formula to explain why the resulting probability is surprisingly small? Applying Bayes' theorem, what if the result is negative? So, it is extremely unlikely you have the disease if you test negative. So, the probability you have the disease if you test negative is Generalized Bayes' theorem. Generalized Bayes' theorem. Suppose that E is an event from a sample space S and that F1, F2, Fn are mutually exclusive events such that assume that P, E does not equal 0 for I equals 1, 2, n. Then exercise 17 asks for the proof. Bayesian spam filters. How do we develop a tool for determining whether an email is likely to be spam? If we have an initial set B of spam messages and set G of non-spam messages, we can use this information along with Bayes' law to predict the probability that a new email message is spam. We look at a particular word W, and count the number of times that it occurs in B and in G, and B, W, and ing, W. Estimated probability that a spam message contains W as P, W, equals NB, W, B. Estimated probability that a message that is not spam contains W as Q, W, equals ing, W, G. Continued. Bayesian spam filters. Let S be the event that the message is spam, and E be the event that the message contains the word W. Using Bayes' rule, assuming that it is equally likely that an arbitrary message is spam and is not spam, i.e., P, S equals 1/2. Note, if we have data on the frequency of spam messages, we can obtain a better estimate for PS. See exercise 22. Using our empirical estimates of P, E, S and P, E, S, R, W estimates the probability that the message is spam. We can class the message as spam if R, W is above a threshold. Bayesian spam filters example, we find that the word Rolex occurs in 250 out of 2,000 spam messages and occurs in 5 out of 1,000 non-spam messages. Estimate the probability that an incoming message is spam. Suppose our threshold for rejecting the email is 0.9. Solution: P, Rolex equals 250 2,000 equals 0.0125 and Q, Rolex equals 5 1,000 equals 0.005. We class the message as spam and reject the email. Bayesian spam filters. Using multiple words, accuracy can be improved by considering more than one word as evidence. Consider the case where E1 and E2 denote the events that the message contains the words W1 and W2 respectively. We make the simplifying assumption that the events are independent. And again, we assume that P, S equals 1/2. Bayesian spam filters using multiple words. Example, we have 2000 spam messages and 1000 non-spam messages. The word stock occurs 400 times in the spam messages and 60 times in the non-spam. The word undervalued occurs in 200 spam messages and 25 non-spam. Solution: P stock equals 400 2000 equals 0.2, Q stock equals 61,000 equals 0.06, P undervalued equals 200 2000 equals 0.1, Q undervalued equals 20. We class the message as spam and reject it. Bayesian spam filters using multiple words. In general, the more words we consider, the more accurate the spam filter. With the independence assumption, if we consider k words, we can further improve the filter by considering pairs of words as a single block or certain types of strings.